Okay, so here's where we're at today. So today we're going to derive the last of the really big equations that you're going to need. Show you where they come from, how they work. I'm going to give you the assignment on this big assignment on planetary motion. I'm going to give that to you today. It is not due until Tuesday when you take the test. Okay? But with that said, do not wait until like, oh, I'll just do it during flex on Tuesday. No, you're going to get hurt immensely if you wait till then, and you're not going to know how to do the problem. So it's not due until that Tuesday, but you want to begin to kind of work through some stuff. So I'll give you that today, and you can't even do some of the homework because there's like some equations that we have to come up with tomorrow and some concepts. All right, so here's the basic idea that you have to get, okay? So if you look at the idea that little g equals big G mass of the Earth over r squared, and that came from the idea that Fg, there's two ways you can calculate Fg. Like let's say, for example, this is the mass of the Connor of your choice. Pick one, okay? Times G would equal big G, mass of the Earth, times the Connor of your choice over r squared, okay? So no matter which Connor that you pick, what's going to happen to the mass of Connor? It's going to cancel out. So at this point, this became one of the most important equations that ever occurred in physics. Because what that tells you is that the only thing that determines the gravitational acceleration of a dropped object is the mass of the object that is falling towards and how far you are away from the center of that object. Okay? That's it. The mass of the object itself, no matter which Connor you pick, drops out of the equation. So then they go, oh, hey, this makes sense. This is why Galileo's experiment, when he took the small cannonball and the large cannonball, he dropped them, they landed at the same time. It's because of this equation. Now, again, is there more force acting on more mass? Absolutely, there is. But more mass has more inertia. You need more force to end up with the same acceleration. So this is one of the most defining equations. They also use this to figure out the mass of the Earth, because Henry Cavendish was the first one to come up with the value of big G. 6.67 times 10 to the negative 11. They knew what the gravitational acceleration was. They had that number. We knew the radius of the Earth. You solve that for mass. So one of the things that you'll see as we go through these equations is that when you look at a table or the internet or whatever, and it says, oh, here's the mass of Jupiter, here's the mass of Saturn, here's the mass of a moon of Jupiter. We don't actually get that data directly. It isn't like, hey, what's the mass of this cup? Oh, I'll put it on a scale. Boom, there we go. What we do is we observe the effects of gravitational fields around these planets or around these moons, and then we solve for that mass. Cool. Okay, so Newton took this a step further. He says, all right, one of his main ideas was the idea that, let's say you're on top of a really, really tall mountain, and this is not to scale, but here's the Earth, and you have a cannon up on top of this tall mountain, okay? So this was his thought process. And you're going to fire a cannonball, and it's going to go something like this. Cool. Any physics person in the world will tell you, well, faster is better. Okay, so let's fire it a little bit faster. Fire it faster, it's going to go out something like this. Let's fire it even faster. And you fire it, and it lands like this. So if you hit just the right speed, what's going to happen?
You get to orbit.
Yeah, it's just going to fall continuously around the Earth. Okay? So when you see people, the International Space Station, the movie Apollo 15, any space thing, you see people floating. You go, oh, they're in zero gravity. Okay? You cannot be in zero gravity and still orbit. Because if you shot this cannon straight out and there was no gravity, the cannonball would just keep going in a straight line. So you cannot orbit unless you were within a gravitational field. Otherwise, it'd be like me trying to swing a rubber stopper around over my head without the string. Well, that's not going to work very well, okay? Because there's nothing to make it orbit because Mother Nature doesn't like circles. So here's a little fact about the curvature of our rock. Is that if you travel 8 kilometers, which is about 5 miles, the Earth curves out from underneath you 4.9 meters. Now, here's the significance of this number. If you look at x equaling 1/2 at squared plus v naught time, okay? Boom, there you go. Well, if I just drop something, initial velocity is going to be 0. And if you let it fall for 1 second and you plug in the math, you get 4.9 meters. So dropped objects at the surface of the Earth fall 4.9 meters every second. If they start from 0, they're going to fall 4.9 meters. So this is why things in orbit have to be traveling at about 8 kilometers per second. Because if you travel 8 kilometers per second, the Earth is going to curve out from underneath you the same rate at which you're falling from the straight line path that you would take. So 8 kilometers per second is about 8,000 meters per second, which is about 5 miles per second. So let me give you an idea of just how fast that is. So imagine you're up here at 53rd and Rock Road, or excuse me, 53rd and Mays. Okay, you're up here at 53rd and Mays. And you're going to go south. Okay, so you're going to get 45th, 37th, 29th, 21st, 13th Street. So you have to be going fast enough to go from 53rd and Mays Road to 13th Street and Mays Road in 1 second. If you're going that fast, you'll be in orbit. Okay? But that's the challenge of getting things into orbit. Because if you're not going fast enough, you're just going to go, boink, and you're just going to fall back. If you're going too fast, you get into weird elliptical orbits, but don't worry about that. So here's the point. For something to be in orbit, you have to have a minimum velocity. And all that's happening is that you're in a state of free fall. Now, we're going to spend a lot of time talking about what we call order of magnitudes. So 8,000 meters per second is like 8 times 10 to the third meters per second. So what you're going to see eventually is that things in orbit around the Earth or things in orbit around the moon almost always have an orbital velocity of 10 to the third. Okay? That's the easy number to remember, 10 to the third. If you ever get an orbital velocity of 10 to the sixth, you have done something horribly wrong. Okay? Worse yet, you get faster than the speed of light, which I've seen that answer as well over the years. Speed of light is 10 to the 8th meters per second. If you ever get an answer anywhere close to 10 to the 8th meters per second for an orbiting satellite, something has gone horribly wrong. Okay, so here's what we're going to do. We're going to take Luke, and we're going to put Luke in orbit around the Earth. Okay? All right, so we're going to launch Luke, and he's going to orbit around the Earth. Luke, is there going to be a centripetal force acting on you as you orbit the Earth? How do you know?
Because I'm going in a circle.
You're going in a circle. And what's the direction of that centripetal force? Inward or outward?
Wouldn't it be?
Yes, you say that with absolutely no confidence. So the centripetal force is going to be acting inward. So here's the things that we could do to make Luke orbit. Option number one, we could tie a string around Luke, anchor that to the earth, and spin Luke around like a rubber stopper. Okay? We could do that. All right? We could do that. Don't recommend it, but that's an option. Option number two, we let gravity do the job. Okay? So let's go with that option. Because tying a rope around Luke probably isn't just very practical. So, here's the story. So what we're going to do is we're going to let the centripetal force acting on Luke be created by the gravitational force acting on Luke. Okay, so we're going to set these two values equal to each other. Okay? And that's the only thing that can happen, is that the centripetal force has to equal the gravitational force. Because there's nothing else. There's no friction, there's no strings, there's no chains, there's no cables, nothing. Gravity has to create that centripetal force. Okay. Now, the first one we're going to use is mv squared over r. And that's going to be the mass of Luke. Okay? It's going to be the mass of Luke. That has to equal the gravitational force, which is going to be big G, mass of Luke, times the mass of the Earth over r squared. Now, no offense to Luke or the Connors or anyone else, but Luke, what's going to happen to you?
Oh, I'm gonna die.
Well, how about you drop out of the equation?
Oh, okay.
Okay? So, here's what's going to be important. I don't have to have the mass of Luke to figure out how fast he's going to go, because that centripetal force is equal to the gravitational force. So when you go through this, I am never going to give you the mass of the satellite. Why?
Because you're mean.
It's irrelevant. Now, does it impact the force that you need to get it into orbit? Absolutely. Okay? Absolutely that does. But in terms of a pure calculation of velocity, period, that type of thing, doesn't matter. Okay? So Luke's going to drop out. So what I've got left is v squared over r equals big G mass of the Earth over r squared. Okay? So I'm going to, guys, I want to get v by itself. So Scooter, what am I going to do? I'm going to get v by itself.
Multiply r for big.
Okay? So I've got all of this. Now, this is a sad day for the pirates. Why? Oh, I'm going to lose one of the r's. Grrr. I'm going to lose an r. So I got v equals the square root of big G over r. Now, I want to do the dimensional analysis to make sure that this is actually a valid equation, because it sounds good. Oh, big G times the mass of the Earth over r. Cool. But if the units don't work out, then we're just dead in the water right from the get-go. So, Andrew, what are the units for big G? Newtons
Yeah, Newton meters squared per kilogram squared.
over kilogram squared. So I've got that up on top. Mass of the Earth is going to be in, the radius of the Earth is going to be in meters. So right away I'm going to lose one of my kilograms, and I'm going to lose one of my meters, right? True. So Deacon, what's another way that I can express newtons? Kilograms meters per second squared. So I took this and just substituted that in for newtons. Okay? That's all I did. Now, I still have multiplying it by a meter, and I'm still dividing it by a kilogram. So now what's going to happen to my kilograms? And you get the square root of,
Meters squared over seconds squared.
which gets you
Meters second.
meters per second. Okay? Now, if that doesn't work out, the equation is dead in the water. If I don't get units of meters per second out of that equation, no matter how cool it is, doesn't matter. So Luke, you're going to be in orbit. So Luke, pick a number between 100 and 200.
174.
Okay. So here's what I'm going to tell you. Luke is in orbit 174 kilometers above the surface of the Earth. Okay? 174 kilometers. Be about kind of 100 miles, kind of the distance from here to Lake Emporia. Okay? Isn't a huge distance, but that's how far. So, when you deal with anything that involves big G, as soon as you see big G, understand this. It is the absolute quintessential usage of the MKS system. Because the only units that you have are seconds, meters, and kilograms. Okay? That's it. So right away, what am I going to have to do with those 174 kilometers? Change that into meters. Promise you, that's the first thing you got to do. So, multiply by 1,000. 1 kilometer, 1,000 meters, I get 174,000 meters. Okay, so that's the first thing. Now, here's the second thing. This distance has to be measured from the center mass of Luke to the center mass of the Earth. Okay? Now, in application, we measure distances from the surface of the Earth up to these things. And here's the reason why. Typically, we use ground-based radar. Well, they're ground-based. They're sitting out on the edge of the Earth. So we're sending a signal from the radar dish back to Luke, and it's getting bounced back. So the data that we're going to have is from the surface of the Earth, because that's where our antennae are. This is where our radars are. But in terms of the data, in terms of our calculations, that has to be from the center of the Earth. So if I ever tell you in the problems, and I'm going to, that a certain thing is a certain distance above the moon or above the Earth, the functional radius you have to use has to be from the center of the moon, center of the Earth, whatever that is, out to that point. Okay? So, what you need to do is take the 174,000 and add that to the radius of the Earth. When you do that, do not round that number. Okay? So, the miracle of your calculators, hopefully you all have these numbers stored in your calculator. So I'm going to take 174,000, add that to the radius of the Earth, give you that answer in scientific notation with no rounding. What'd you get?
6.5, wait, 6.5453. Yeah,
Times 10 to the 6th?
yeah.
Cool. Do not round that to 6.5. No, bad. Okay? You keep all of those digits. Okay? We're going to round when we get to the end. So let me kind of let me dispel some common misbeliefs. So everybody thinks, oh, things are in orbit above the Earth. They're like way out here. Okay? On this scale, if this was the size of the Earth, 174 kilometers would be about a ½ inch above the surface of the Earth. Okay, that's all it would be. There's nothing magic about outer space in terms of a radius. We just have to get outside of our atmosphere. Because if you try and go as fast as at that 8 miles or 8,000 meters per second, within an atmosphere, you're going to instantly vaporize something because it's going to be going so fast that it's going to create so much friction that it's going to vaporize. So the only thing magic about space is that it's outside of our atmosphere. If we didn't have an atmosphere, we could launch satellites just high enough to clear the Rocky Mountains or whatever mountain range you're going to go over. That's the only thing we would have to do in terms of height. Just enough to clear the mountain ranges. So, but if we didn't have an atmosphere, there really wouldn't be much of a point anyway. But when you look at our atmosphere, the magic of space is that we get it into the vacuum. Though these equations only work if you're in a state of free fall outside the atmosphere of the Earth. But here's the problem, is that when you do re-enter the atmosphere, you heat up really, really quickly. And this is, so if you've ever seen like a shooting star at night, okay, that comes from a piece of rock, meteor, something like that, that's entering our atmosphere. It gets superheated, you see the streak across the sky. Same thing happens like when spaceships go through re-entry. The most violent and dangerous part of that re-entry is when you're being slowed down by the collisions with our atmosphere. So, like it literally, it looks like a fireball. Because, and when we get into energy, we'll talk more about this, but basically what you're doing is that you're trading kinetic energy, which is the energy of motion, and you're trading that into thermal energy. So that's what makes you slow down. So basically you're using thermal energy as a brake to slow that down. But, and that's great as long as it works, but then if you get a breach in that system, that's when bad things are going to happen. Okay, so at this point, I want to calculate the velocity of Luke, but do not touch a calculator. Do not touch your calculators for now, okay? We'll deal with this later. So I've got velocity is going to equal big G, 6.67 times 10 to the minus 11th newtons meters squared over kilograms squared, times the mass of the Earth, 5.979 times 10 to the 24th kilograms, divided by the radius of 6.5453. Now, all I want to do is something called order of magnitude, right? Order of magnitude means that you really don't worry about the numbers themselves, you just worry about the exponents, okay? Literally, that's all we're going to worry about. So Thatcher,
Yep.
10 to the negative 11th times 10 to the 24th gives me what? 10 to the 13th. So up on top, I have 10 to the 13th, okay? I'm going to divide that by 10 to the 6th, which is going to get me 10 to the, divide by 10 to the 6th. I get about 10 to the 7th. But then I'm going to take the square root of that, which if you look at everything else, is going to get you something around 10 to the 3rd. So any velocity that you calculate, near Earth orbit, moon, whatever, that velocity should be something times 10 to the 3rd. If you get 10 to the 4th, 10 to the 2nd, 10 to the 5th, you have done something horribly wrong, okay? Now, here's what you're going to do wrong. I promise you, and you all laugh, you go, Mr. Burkamp, we won't do that. Yes, you will. Here's what you're going to do wrong. I'm going to tell you that Luke is orbiting 174 kilometers above the Earth. Mistake number one, you're just going to come in here and go, oh, I'm just going to put 174 as my radius and blissfully write down 174. Okay? Seen that one happen. Then you're dividing by a really, really, really small number and you get a really, really big velocity. Situation number two, you remember this inner voice says, oh man, Burkamp told me I have to convert to the MKS system. So then you take the 174, you do multiply it by 1,000, you have 174,000, and you put that number in. Still too small of a radius. Okay? Then you're going to go do the happy dance, and you're going to do all these numbers, and then you're going to forget to take the square root of it. Okay? Been there, seen it all. And you all sit there and go, Mr. Burkamp, we won't make those mistakes. Don't be silly. Yes, you will. Okay? But the beauty of it is that when you get done, you know you should end up at something times 10 to the 3rd. Now, trust me. Do this calculation. Make sure you know how to use that calculator and make sure your numbers are stored correctly. So right now, I would highly recommend get out that calculator. Make sure you can take big G times the mass of the Earth divided by 6.5453 times 10 to the 6th, and then take the square root of that. And then give me that answer in scientific notations.
$7.81 times 10 to the third.
7.81. Cool. Okay? It matches, right? 7.81 times 10 to the third. A little bit slower than the 8,000 because that 8,000 is right at the surface of the Earth, or a little bit above the surface of the Earth, so that's going to be a little bit smaller. Now, Luke goes, Mr. Burkamp, that's awful fast. I'm not feeling comfortable going that fast. I want to go, I'm a little bit slower pace, okay? I'm more laid back. I'll play the guitar. I need to chill out. So, what can Luke do to drop that velocity?
Move further away.
Why?
Because the radius is on the bottom, so it'll increase your power answer.
Yeah. So if Luke goes, man, this is fast. Not digging it. I'm going to boost it into a higher orbit. So if I boost it into a higher orbit, I'm not going to change big G. I'm not going to change the mass of the Earth. The only variable is going to be the radius. So if we boost Luke into a higher orbit, his velocity is going to become less. Cool with that. Okay. Now, at this point, we know that centripetal acceleration equals v squared over r. True?
True.
We have Luke's velocity. Could we find the value of Luke's centripetal acceleration?
Yeah.
Yeah, because now we know how fast Luke is going, and we know the radius. So let's do that. So, somebody take that answer, 7.81 times 10 to the third meters per second, and that's going to get squared. And then I'm going to divide that by the 6.5453 times 10 to the sixth meters. Now, order of magnitude, Deacon, what's going to be the order of magnitude of this answer?
Should be 10 to the 0.
Yeah, 10 to the 0. It's not going to be a big number, okay? Because I got 10 to the 6th divided by 10 to the 6th. I'm going to get a small number, okay? So what do you get? 9 something. 9.31? Okay? Now, I want you to, right now, forget that that calculation exists. It's gone. We never did that calculation. Okay? It's not there. We never did this. What calculation? Exactly. Now, Luke picked as his radius, what did you pick as your radius, Luke?
174.
174. Now, I want you to have this visual. Stay with me here. Here's the Earth. We're going to take a ladder and we're going to set that and we're going to build a tower that's 174 kilometers tall. Okay? 174 kilometers tall. Cool. Now, Luke is going to climb up to the top of that. So here's what I want you to think through. Right now, you can't get this experience, but trust me. I'm spinning on this Earth. Which part of me is moving faster? My feet or my head? My head. Why?
Bigger radius.
Bigger radius. Not by much. It isn't like, whoa, I can feel that. Okay? So we go here. But when I stand up, the top of my head is moving a little bit faster than my feet. So imagine that we're going to build this tower about 100 miles tall. Okay? Big tall tower. And Luke's going to climb to the top of that, and he's going to be standing up there going, yes, here I am. Right? And he's going to be going pretty fast around that. Right? Okay? pretty fast. So here's what I want you to look at. Imagine Luke has a baseball, as Luke is wont to do. Okay? And Luke is going to drop that baseball, and he's going to let it fall. Will the ball accelerate?
Yes.
Why?
Gravity.
He's still within the gravitational field of the Earth. He's not in orbit. He's just standing on top of this really tall tower. That's 174 kilometers tall. Do you think the acceleration due to gravity is going to be bigger or smaller than 9.8 meters per second squared? Small. Because at the surface, what's your acceleration? 9.8. So we're going to be up there a ways. So we can actually calculate that value, and this is what we're going to do. We know that little g equals big G mass of the Earth over r squared. And then where does that radius have to be measured from?
The center of the earth.
Center of the Earth out. Okay? So we know what big G is. And by the way, when you're doing these problems, you don't need to write out 6.67 and the mass of the Earth. You can just put big G mass of the Earth. Okay? I know what those are. You don't need to write out the numbers. Okay? You can just simplify it. So you can just come in here and go big G, mass of the Earth over. Now, that still has to be measured from the center of the Earth out to that point. Okay? I can't use the 174. It still has to be from the center of the Earth out to that point, which is that 6 point, whatever that is, 5453 times 10 to the 6 meters. And that's going to get squared. So, crunch the numbers. Let me know what you get. What'd you get?
9.82.
9 point what?
82.
No.
Yeah, that makes sense.
What'd you get?
You got 9.3.
Oh, you got 9.3.
9.31.
Oh, 9.31.
It's the same.
Oh, how cool is that?
What?
Whoa!
That's crazy.
It's the exact same number. So the gravitational acceleration, wait for it, is the exact same as the centripetal acceleration. Coincidence? I think not. Why? Why are those two numbers the same?
Because force gravity equals force centripetal force.
Oh, the gravitational force is creating the centripetal force. Now, so we're going to look at this from a couple of different ways. So at the end of the day, we said that the gravitational force equals the centripetal force. So the simplest way to calculate gravitational force is the mass of Luke times G. The simplest way to calculate centripetal force would be the mass of Luke times his centripetal acceleration. No offense, Luke, what's going to happen to you?
I go bye-bye.
They go bye-bye. So guess what? Little g equals your centripetal acceleration. Okay? What's that? Now, if Luke climbs to the top of that tower and he has a 1 kilogram mass, what is a 1 kilogram mass going to weigh at the top of that tower? 9.31 newtons. Why? That's the gravitational acceleration, right? So a 1 kilogram mass, if Luke is in orbit, is going to weigh less, okay? If you could stand on top of that tower. So there's two different things though that you have to visualize. If Luke's just standing on top of the tower and he's just going to drop it, he's going to notice it falling because he's moving with the Earth. But if he's in orbit, traveling at 10 to the 3rd meters per second, and he drops it, it's still going to fall, but Luke's going to be falling with it, and it's going to appear to float. But no matter what, here's what I want you to see. If I ask you to calculate the gravitational acceleration at some point above the Earth, what else am I asking you to calculate? So the centripetal acceleration. So if you ever know one, guess what?
You know the other.
You know what the other one is. Okay. Andrew, stop that camera.